In the third unit of this lecture, we're finally going to introduce the backpropagation algorithm. Remember that most maximum likelihood problems don't have a closed form solution, and therefore we need to utilize gradient-based optimization techniques. And in order to use such gradient-based optimizers, we need to find the gradient of the model of this negative log likelihood with respect to the parameters W of the model. Or more generally, what we want to do is we want to optimize a loss function with respect to the parameters W. So here we have a loss function indicated by this calligraphic L that depends on a data set. Here this Y in boldface and X in boldface indicates the entire data set, again stacked into rows, and the parameter vector W. And if we write this out in terms of the individual data points, we get the gradient of the sum over all data points, because we assume the data is drawn IID, over the individual loss functions. So this is this term here, L, for each individual data point, Yi, Xi, and W. Right? And N indicates the number of data points in our data set. And because the gradient operator is linear, we can pull this through the sum here. So this is equal to the sum over all the data points of the gradient of the loss function with respect to the parameters W. Right? So in this notation, I've used Xi and Yi as the data set with n elements. In the following, we're going to consider the computation of gradients with respect to a single data point. So we're only going to look at this expression here. If we want to find the gradient with respect to the entire data set, we simply need to sum over all of the gradients that we have estimated for each individual data point. So basically, from this expression here, we get a vector, which is the gradient of this loss function, the scalar valued loss function with respect to all the parameters that we have. That could be millions in our neural networks. And then we have such a gradient vector for each, or we calculate such a gradient vector for each data point I. And then we sum up element-wise these gradient vectors over all the data points in order to obtain the gradient vector with respect to the total loss function over the entire data set. And once we have that, we have found the gradient, we can take a step into the gradient direction, which is called gradient descent. Right? So the gradient with respect to the entire data set X is obtained by summing up all the individual gradients, all these individual gradients. And on the following slides, we will look at how we can actually compute these gradients efficiently, which is non-trivial because we have in large neural networks, we have millions of these parameters. So it's important that this computation is very fast, because we need to do a lot of gradient descent steps in order to arrive at the local minimum. Okay, so in order to understand the backpropagation algorithm, there's basically just one rule that we have to understand, and that's a rule that we already knew from a high school, and that is the chain rule. And the chain rule tells us that if we have a concatenation of two functions, f and g, so here we have a function f that depends on the result of a function g, and that function g depends on some value x, then the derivative of that function f with respect to the parameter or the variable x is equal to the derivative of the function f with respect to the derivative of the function g times the derivative of the function g with respect to divided by the derivative of the function x. Right? So this is the simplest form of the chain rule. Now, what we're also gonna need in this lesson here is the so-called multivariate chain rule. And the multivariate chain rule is concerned with compositions of functions where in the argument of a function we have a set of functions, and each of these functions here depends on the same variable x. Right? So that's the difference between these two. Here we just have f of g, and here we have f of g1 to gm. And all of these functions g1 to gm depend on the same variable x. And what we want to compute is the derivative of this composition of functions with respect to the variable x. And what the multivariate chain rule tells us is that this derivative is simply the sum over all the individual chain rules here. So that's the derivative of f with respect to gi times the derivative of gi with respect to dx. And that's summed up over all the functions I. So these two rules are really the only thing that we're going to apply throughout this lecture. Okay. So let's look at the most simple form of the backpropagation algorithm, one of the most basic examples, which is basically just the chain rule in a slightly different form. For now, we're going to not make any distinction between node types. Remember that in computation graphs we have defined input nodes and parameter nodes and compute nodes. For now, we're going to just consider nodes. So we have all the nodes in red here. This is the color that we've used for compute nodes before. But we're not going to make any distinction at this point. The only thing that we want to do is we want to compute gradients with respect to any of these nodes. So we want to compute gradients of this final output node, which we call L here for loss. Actually, in this case, it doesn't need to be a loss function. It could also be C, for instance. Right? It's not necessarily a loss in this simple expression, but because we're going to consider losses always at the output as the output node in the following, I've used the loss symbol here as well. And what we're interested in is the gradient of this loss with respect to the loss itself, or the variable y, or the variable x. Okay, so this is a very simple computation graph where we have y depending on x and L depending on y. And the expression that we want to formulate here is simply L equals 2 times x squared. And we have decomposed this in the sense of atomic operations in a computation graph, as we've discussed in the last lecture, as follows. In the first step, we calculate y as the square of x. And in the second step, we calculate L as 2 times y. So composing the two, we obtain 2x to the power of 2. Okay. So now what we're going to do is we're going to, after running this forward pass, as after actually calculating the value of L for a particular input x, we're going to run a so-called backward pass. That's where the name backpropagation is coming from. So we're first going to run a forward pass in the direction of the black arrows in order to compute L from the input x. So assume x would be 1, then we would have L equal 2. And then we're going to run a backward pass. I will indicate this in the following slides and with blue arrows, while we backpropagate gradients from the output node, which is always L in our case, to each individual node, such that at each individual node we can read off the gradients with respect to that node. The gradients of, I must say, L with respect to each of these nodes. That's what we're interested in. Gradients of L with respect to any variable in this computation graph. And I'm going to use two different colors here for indicating two different types of quantities. I'm going to use a red color for backpropagated gradients, and I'm going to use blue color for local gradients. Gradients that are locally computed based on these assignment formulas here, based on the local functional form that is present at a particular node. So the backward pass starts at the output node L, and it computes gradients backwards. The first thing it does, it computes the gradient of L with respect to itself, which is obviously 1. Right? So the partial derivative of L with respect to L is 1. Note that here in this notation, we're always abusing the derivative operators a little bit. So we're always using partial derivative to indicate that we're computing a derivative with respect to any possible parameter within that entire expression, even though that that might be actually a, that might only occur within an inner function of that expression. So whenever I'm gonna write partial of L with respect to, or divided by partial of any variable, I mean the gradient of that output node with respect to any of these variables inside. Okay, so in order to compute now the gradient of L with respect to y, which is what I'd like to do first, and which I write at the bottom below y here, what I need to do is I need to apply the chain rule, which is I need to compute the gradient of L with respect to the gradient of L times the gradient of L with respect to the gradient of y. This looks a little bit ridiculous here, right? Because what we're really interested in is only the gradient of L with respect to gradient of y. But you will see that writing it in that form makes sense if we go further back in this simple computation graph. Okay, so this is obviously correct, right? If the partial L here cancels, so this is exactly the same as the gradient of L with respect to the gradient of y. So what is the gradient of L with respect to the gradient of y? Well, it is 2, right? Which we can see from this expression here. So the gradient of L with respect to the gradient of y is L with respect to y is the gradient of L with respect to L times the gradient of L with respect to y, which is 1 times 2, which is 2. So we have now backpropagated the gradient until here. So now we can do one step further, right? So we're going from the second expression here. So we're going backwards. Now we're calculating the first expression, the gradient with respect to the first variable, which we have in the forward pass computed first. And we do exactly the same thing. So now what we do is we compute the gradient of L with respect to x. So this is what we want to compute. And this is exactly the message that we're sending here is exactly, again, the chain rule. It's the gradient of L with respect to y times the gradient of y with respect to x. Obviously, this is correct. This is the same as the gradient of L with respect to x, right? Because the partial y here cancels. Now, the gradient of L with respect to y, we have already computed. This is the backpropagated gradients from this node here. We have backpropagated it here. So this is something we have already computed in the previous iteration. So the only thing we need to do is now we need to multiply the local gradient, which is the gradient of y with respect to x, which is 2x. And this is what happened here. So the gradient of L with respect to x equals the gradient of L with respect to y times the gradient of y with respect to x. And that's the gradient of L with respect to y. So that's what we have calculated at this point times 2x, which is the local gradient. And now we have found the gradient of L with respect to x. And you can imagine that we can go further backward in such a chain or in such a tree in order to backpropagate gradients even further. What we're ultimately interested in is to backpropagate gradients, of course, to the weights of a parametric function, such as logistic regressor or a neural network. We'll see that in the following slides. So that was maybe a little bit abstract, so let's make it very concrete. So what we do here is we plug in the actual numbers, right? So the gradient of L with respect to L is 1, so we plug it in here. And then we multiply it with the gradient of L with respect to Y, which is 2. And 1 times 2 is 2. So this gradient here, the gradient of L with respect to Y, which is what we have calculated here, we have backpropagated it here. You can imagine these arrows backpropagating the gradient that they compute, like from the previous node and the local gradient to this location here. So we just copied here. Now this is then coming up here, right? This is the same expression here. And we multiply it again. We multiply the backpropagated gradient, now the 2 in this case, with the local gradient, which is 2x. So we have 4x. So we send this gradient 4x to this location. So we get 4x here. And as you can see, the gradient of L with respect to x is obviously 4x. Right? Of course, when you implement this on a computer for doing an actual forward and a backward pass, you will fill in actual values for x. Right? So for the current input and output, you know the values, and you also know the values for the current state of the parameter vector. So for x and y and for w, we don't have w here yet. We'll see that on the next slides. But for all the values at a particular iteration, we have we know the values. So we will always insert the actual gradients, not these symbolic gradients here, but we will actually have real values that we input here. Okay, so we made it a little bit more concrete. Now let's make it a little bit more abstract again. What I've done here is I've replaced the concrete definition of these functions here with abstract functions. So what I write here is, instead of y, it's just a function y of x. Instead of L, it's just a loss function L of y. So the expression reads like this: L of y of x. Right. So this is the most generic form I could express this particular computation graph with. And in this more general form, I have the backward pass as the gradient of L with respect to y is the gradient at node L times the local gradient. And because this is always 1, I have just the local gradient here. And then the gradient of L with respect to x, this guy here, is the gradient of L with respect to y, so what I've computed previously, times the gradient of y with respect to x, the local gradient here, by reversing this arrow. Okay, so this was the most simple example. It was basically just applying the chain rule twice. So let's look at a slightly more difficult example now. And this is an example where we have a fan-out bigger than 1 situation. Fan-out means the number of connections that are outgoing from a particular node. Before, we had a chain, so every node was having 1 outgoing connection. Now in this case, Y has multiple outgoing connections. Y sends to U and to V. So we're looking in this particular case here at this loss function. It's L of U of Y of X and V of Y of X. So the forward pass in this example looks as follows. Y is computed as Y of X. So it's this function of X that we evaluate at X, the input X. And then we evaluate u of y and v of y. These are these two here. I use the same iterate here in this enumeration because they are processed at the same time, basically, right? So they're branching out and processed at the same time. And then we have L, which depends on both u and v. Okay. So let's compute the backward pass now. Starting again with the output node L, we have the gradient of L with respect to u is the gradient of L with respect to L, which is 1 times the gradient of L with respect to u. And similarly, the gradient of L with respect to v is the gradient of L with respect to L times the gradient of L with respect to v. Okay, so far so good. This was step 3. Now let's look at step 2, going one step further. The gradient of, what is the gradient of L? This is the gradient of L with respect to y. Now the situation is different from before. In this case, both u and v send gradient information to this variable here, to this variable y. Namely, u sends the gradient of L with respect to u. This is what has been computed at the u location times the local gradient from u to y. And similarly, v sends the gradient of L with respect to v. This is what has been stored here in the previous iteration of the backpropagation algorithm times the local gradient from v to y. So what should this expression then read like? Well, remember the multivariate chain rule that we've seen before. We have exactly the same situation here, right? So if you look at this loss function, we have a loss that depends on y via two functions, u and v. Both u and v depend on y. So if I ignore the argument of y, x here, this is what this loss function would read. L of u of y and v of y. So what we know is that from the multivariate chain rule, the gradient of L with respect to y is simply the summation of L with respect to u and u with respect to y plus the gradient of L with respect to v and v with respect to y. So this is simply a local application of the multivariate chain rule at one particular node. And this is what I've written over here. Of course, both these terms have local contributions in blue and these backpropagated global contributions in red. So it's important to remember whenever we have such a fan-out situation, whenever one variable sends to multiple variables, whenever we have an expression like this, we need to, in the backpropagation pass, basically whenever we have a head-to-head relationship, when there is two arrowheads that are pointing to the same variable, we need to sum up all the gradients. This is what has happened here, or here. That's basically it. And then in the final step, because we're not done yet, we compute the gradient of L with respect to x simply as we know it already as the gradient of L with respect to y. This is basically what we have computed in the previous step as this summation here times the local gradient of y with respect to x. Of course, this is an abstract example where we don't know the precise form of each of these individual functions, so we cannot look into this further unless we would specify this function in detail. So now we are basically ready to implement the backpropagation algorithm. How could we implement that backpropagation algorithm in Python? Well, a convenient way to do so, and this is also what the educational framework does, is to consider each variable or node as an object that has certain attributes. For instance, the value and the gradient. So let's say we have a variable x that has a value. These values are computed in the forward pass, and it has gradients which are updated in the backward pass. So the values, they are computed in the forward pass. This is basically just writing out this program here, the sequence of assignments in Python, where we have the value of x is basically the input. Let's say the image or whatever signal comes into the model as an input. And then we have y. The value of y is the function y evaluated at x value. And then u value is the function u evaluated at y value. And then v is the function v, this one here, evaluated at y value, which has been computed here. And then finally we have the loss function, which is simply depending on an evaluation of the loss function L that depends on the value of u and the value of v, which have been computed here. Okay. Similarly, we can look at the backward pass. Again, I've used the red-blue notation here to indicate if it's the backpropagated global component of the gradient or if it's the local contribution of the gradient. So how do we implement the backward pass? Well, first of all, we would set the gradients to 0 because we're gonna additively update them. So we start by setting all of them to 0. X, y, u, and v grad are set to 0. And then we start with the gradient of L with respect to L, which we know is 1. So this is this term here. This is 1. Whenever I use this notation L grad or U grad, what I mean is basically the gradient of L with respect to the variable that has this attribute grad. So for instance, Y grad is the gradient of L, of the loss, of the output node with respect to the variable Y. Okay, so now we've initialized with L grad equals 1. And now we can calculate U grad. So this is this equation here as L grad, which is 1, times the local gradient L with respect to U evaluated at the value of U and V that have been computed in the forward pass. Right? So it's important to note here that we need the values that have been calculated in the forward pass because we need to evaluate the gradient at these particular locations. Right? So it's really a concrete value that the evaluation of the gradient at a particular value returns. The gradient itself is a function and it's evaluated at u and v in this case. Similar for v, it's the gradient of L with respect to v, which is a function which is evaluated at the value of u and v. And then we have y, and this is now this special situation where we have a sum due to the multivariate chain rule that we've seen before. So what we do here is simply we execute this line twice. Once we add the gradient for u and once we add the gradient for v. Both the global component multiplied with the local component, which is evaluated at the value of y. And then finally, we update the gradient of x as the gradient of y times the local derivative of y with respect to x, evaluated at the value of x. Okay, so let's look at a slightly more real example in the sense of machine learning. And this is the example that I'm showing here is the logistic regression example that we've already seen before, also in the context of forward propagation in computation graphs. right? So this is the formula that we've already seen. BCE denotes the binary cross-entropy loss. Right? And what happens here is basically simply we have a affine function u that linearly combines W0, W1, and X. This is this linear function u. Then we have the sigmoid operation here that returns y hat and takes in u. And finally, we compare y hat to y using the binary cross-entropy function, which is defined like this. Here on the top, for space reasons, I've used just the abbreviation BCE. And so this is basically the entire expression on the left, written in a single line. Okay, so this was the forward pass. So let's look at the backward pass now. In particular, what we want to do is, in this case, and this is different from before, we want to calculate the gradients, but we're not interested in the gradients with respect to any variable in this graph. For instance, we're not interested in the gradients with respect to these green input variables here. We could calculate them, and sometimes we really do, like in the case of style transfer, where actually the input is modified. And that's the beauty about the backpropagation algorithm, that it can compute the gradients with respect to any variable, can even compute the second derivative by executing it twice. But in this case here, when we're interested in training the parameters and learning the parameters of a logistic regression model, we're really just interested in backpropagating the gradients from L to W1 and W0 so that we obtain the gradients of L with respect to W1 and W0, which are then used in the gradient-based optimization inner iteration loop in order to update the gradient, the parameters of the model. Right, so here you can see we have used now the same notation that we have defined in the previous unit, where green are input variables, orange are parameter variables, and we are interested in the gradients with respect to the parameters, and red are the compute nodes. So let's apply the backpropagation algorithm to this example. Again, we start with the gradient of L with respect to L, which is 1 at the output node. But we're not backpropagating to y, we're just backpropagating to y hat in this case. So what is the gradient of L with respect to y hat? Well, it's the gradient of L with respect to L, which is 1, so this goes away, times the gradient of L with respect to y hat, which is simply this expression here. So if you calculate the gradient of this term here, you end up with this expression. Okay, then in the second step, what we do is we compute the gradient of L with respect to u, which is the gradient of L with respect to y hat that we have calculated in the previous step, times the local gradient of y hat with respect to u. And the gradient of y hat with respect to u, this is simply the sigmoid, is the sigmoid of u times 1 minus the sigmoid of u. I recommend to do as an exercise both of these derivations, which are really simple but also quite instructive, so that you see how you get from this expression to this expression and from this expression to this expression, which are both the gradients of these expressions. Okay, so we have relatively compact terms now for these local gradients. And what we finally do is we compute the gradient of L with respect to W0 as the global contribution, the backpropagated gradient L with respect to u from the previous iteration of the algorithm, times the gradient of u with respect to W0. And the gradient of u with respect to W0 is 1. So we end up with the gradient of L with respect to u. And we can do the same thing for W1. The gradient with respect to W1 is the gradient of L with respect to u from the previous iteration times the gradient of u with respect to W1. The gradient of u with respect to W1 is x. So we end up with L with respect to u times x. And again, of course, when we apply the backpropagation algorithm on a computer, we calculate the values in the forward pass, and then we calculate the gradients in the backward pass, and immediately evaluate them at the values that we have calculated in the forward pass. Okay. So in summary, what we've learned in this unit is we can write mathematical expressions as a computation graph, and that decomposes complex expressions into much simpler computations that are tractable, and where we can apply efficient dynamic programming to solve for both the values in the forward pass and the gradients in the backward pass. Right, so the values are efficiently computed in the forward pass, and the gradients are efficiently computed in the backward pass. And this is really why backpropagation is still the primary workhorse of deep learning today, because it allows us to calculate the gradient, in particular using parallel computing hardware. This is an algorithm that is highly parallelizable. We can calculate the gradient of an objective function, of a loss function, with respect to millions or sometimes billions of parameters in the matter of just a few seconds or minutes. Right, so this is the forward direction, and this is the backward direction. What we've also seen is that multiple incoming gradients are summed up in the backward pass. If we have this head-to-head relation in the backward pass, it's not happening here, but it was happening in this case before. And it's also happening, for instance, in the case of a multi-layer perceptron, where we have fully connected relationships between adjacent layers in a neural network, such that there is a lot of nodes that send to multiple nodes in the next layer. And this is the summing up is a consequence of the application of the multivariate chain rule. And the really beautiful thing about this is this application of the chain rule and this modularization is that each node must only know how to compute the gradients with respect to its own arguments. This is basically what we had in blue on the previous examples. We only need to calculate these local gradients. We don't need to know anything about any other nodes in the graph. It's very decomposed. It's always good if we can decompose things, right? It makes things simpler. Yeah. And then finally, a final remark, when we now want to apply this forward-backward pass, this backpropagation algorithm to optimize the parameters of a model, such as a logistic regressor, of course, we need to calculate the gradients over the entire data set. And what we've just discussed is only the calculation of the gradients with respect to a single data point, right? We have taken a single data point and we passed it through this computation graph in order to compute a loss for that single data point. In this case, xi, and then compared it to yi. But what we need is we need the gradient of the entire objective function, which, assuming IID data, is simply the sum over all the data points of all the gradients. So what we need to do effectively is we need to apply this backpropagation algorithm many times, namely as many times as we have data points in our data set, in order to obtain the gradient of the loss function, the overall loss function of the entire data set with respect to the parameters w. So we apply the backpropagation algorithm n times, we get the gradient, and then with this gradient we can do one gradient update step in the inner loop of the gradient-based optimization algorithm. A little disclaimer, so far we've only discussed the backpropagation algorithm for scalar values, but in the next lecture we'll see how we can apply the backpropagation algorithm on arrays and tensors.